Welcome back to ECE 320A. We are in Unit 3, and in this video we want to pick up where we left off last time. Last time we just discussed the wirings of sources and loads, be that in a Y configuration or a delta configuration, and we mentioned the 4 different possible combinations of interconnections that could exist in that with those wirings of the source and the load. And what we want to do now is simply show those 4 different interconnection patterns, the YY, the Y delta, the delta Y, and the delta delta, and start to become a little bit more comfortable with some of the definitions and terminology that will be used in the remainder part of this unit. Let's go ahead and get started with the first interconnection pattern, and this particular pattern is one that we probably will sort of feel as our bread and butter. We probably feel most comfortable with it, but you can see now that the source is connected in a Y, and we've included the source generator impedances with the subscript lowercase g, a, g, b, g, c for the ABC phase impedances. We have the source generator voltages, and those are labeled V sub A prime N. So the A prime is a node between the generator impedance and the terminal of the generator itself, which we're labeling as A. Likewise for the B phase and the C phase, those terminal labels, here is what you would have access to in terms of the generator. You would have these generator terminals. Embedded inside there are the generator voltages, A, B, and C, and the impedances that we're lumping into Z sub GA, Z sub GB, and Z sub GC. We then have the transmission lines for all 3 phases. The A phase transmission line is capital Z sub lowercase l A. And we have then the loads, A, B, and C phases, with the Y configuration or Y wiring at the load. So this is our YY configuration, and I've labeled some currents in blue, in green, and some voltages in red. At the currents, I hope you can see that I now have capital I sub little a, capital A, and that is going to be our A phase current in the transmission line. But I hope you can actually see that this current not only is going through the transmission line, but it also continues and goes through the load itself in this particular configuration. That current doesn't have to branch off before it actually goes through the A phase of the load. And because of that, we can actually call this particular current the A phase load current. And that's true in this YY configuration, that current in the transmission line is actually going through the A phase of our load. That won't be true in general, but here I sub little a capital A is the current that goes through the A phase of the load. Then let's talk about at the load and the load impedance, capital Z sub A. We'll only sort of focus on one of these phases. All the others, I hope you can see that I sub BB, and I may just say BB and not say lowercase uppercase. I sub BB is also a line current, but it's also the phase current for the B phase. And I sub CC is the C phase current, and it's also the line current in this configuration or interconnection structure of YY. Now, if we go to the load side and look at the voltages, I've now labeled capital V, capital A, capital N, and that's the voltage dropped from the positive terminal of the A phase to the neutral terminal, capital N, in the A phase. And not only does it have that voltage, but and since it's the voltage across the A phase load impedance, this is the A phase load voltage, and that's V sub AN. And we're calling it the A phase load voltage because that's the voltage across the A phase of the load. And that is going to be different from the voltage that actually exists between this terminal and that terminal, capital B. So the voltage dropped across terminal capital A to capital B is V sub AB, and that's not the same as the A phase load voltage in this particular configuration. And we'll have to be making these kinds of distinctions as we work through these different interconnection patterns. So in this case, the A phase load voltage, V sub AN, is not the same as the voltage dropped across the load terminals, capital A and capital B, which is V sub AB, and we might call that the line voltage at the load because it's between the transmission lines. The A phase load voltage is not the same in this particular interconnection pattern as the line voltage across terminals A and B. The B phase load voltage is capital V sub Bn, and the C phase load voltage is capital V sub Cn. I hope that's somewhat clear on the distinction between the A phase load voltage and the transmission line voltage or the line voltage V sub AB. Those are not the same. And you can do a KVL to convince you of that. Here, this would be the negative terminal of V sub AB, and this would be the positive terminal. And you can now write a KVL equation going into the negative terminal of VAB, and we would have minus VAB, these are all phasors, plus V sub AN minus V sub BN is equal to 0, and we'll use that relationship to define a relationship between the line voltage and these different phase voltages. So this is the YY configuration. Let's now go to another interconnection pattern. So here, I hope it's clear. And before we move on, I just saw something on the next pattern that triggered this. Note that V sub AB is not equal to V sub AN. So the A phase voltage is not equal to the A transmission line voltage. Here we have a Y source, that's the one that we will denote first, connected to a delta load, and we also have our transmission line impedances shown. Here we have our A phase line current, and what else do we have? Well, now we want to find the A phase load voltage. Well, that's now going to be across the impedance of our A phase, and now it's in a delta configuration. This particular voltage, V sub capital AB, is the A phase load voltage. And note that that's actually the voltage across terminal A and terminal B. That's this particular voltage drop that we had defined in the previous interconnection pattern, but now here our A phase load voltage is in fact equal to the A phase line voltage. But what can we say about the A phase load current? In this case, the A phase load current will be passing through the A phase load impedance, which is Z sub AB. This I sub AB is our A phase load current. What is our B phase load current? Well, it's now going from terminal B to terminal C. This is now I sub BC, and I sub CA goes from terminal C to A at the load. This is a delta configured load, and the B phase load current is not the same as the B phase transmission line or line current. Here is the transmission line B phase current, and it now goes into this particular node, but now it has to be somehow divided among I sub AB and I sub BC, and we can find that by performing a KCL at that particular node. In this case, I hope it's clear that the A phase line current, which we're calling I sub AA, that's the transmission line current, is not the same as I sub AB, because as I sub AA comes in here, look what happens at the A terminal. It now has to be divided among I sub AB and I sub CA. And we would have to do that algebraically in being consistent with Kirchhoff's current law. So in this case, in this load configuration of a delta, the line current, A phase line current, is not the same as the A phase load current. In the Y configuration of the load, the A phase line current, I sub AA, was in fact, so here this is also the A phase line current. That's the same as the A phase load current. Do you see how you need to keep track of labeling and terminology with these different interconnection patterns? Here's the delta to Y configuration, meaning our source is now a delta source and our Y is the load wiring diagram. The A phase load voltage, that is actually going to be V sub AN. The line voltage at the load terminals is different from that. It's now this voltage from the terminal A to the terminal B, and that now has to, by KVL, has to be algebraically combined with V sub BN and V sub AN to produce the A phase line to line voltage, or the line voltage at the terminals of the load, and that's in contrast to the A phase or the B phase load voltage in that configuration. But I hope you can see that the line current, the A phase line current, is in fact the A phase load current. But the A phase line current is not the same as the A phase generator current because of this node, and we see then that the transmission line A phase current is consisting of I sub, I'm not sure I even want to denote this, but this is now I sub AB, and this current would be I sub CA. And those two combine to create I sub AA in this particular configuration. And finally, we have the delta-delta configuration. Here, what is our A phase load voltage? That's V sub AB. We do not even have a V sub AN in this delta wired load. What's our A phase line current? That is I sub AB. I'm sorry. What's our A phase load current? So hopefully I'm being consistent here. The A phase load current is I sub AB, and the A phase line current is I sub AA, and those are not the same because we would have to algebraically perform KCL and incorporate I sub CA in with I sub AB to produce I sub AA. Those are the different interconnection patterns, and the terminology that we have started to introduce is A phase line current, A phase load voltage, A phase load current, and A phase line voltage at the terminals, or it could be A phase load voltage at the source. A phase at the terminals of the source. What is the line-to-line voltage at the terminals of the source in the A phase? That would be this voltage in this configuration, V sub AB. So we have to keep all of these different terms clear, and we'll try to enforce that or reinforce that as we work through more videos.